So last Thursday, we talked about analyzing reaction equations and using the technique of statements of equality to convert between a known and an unknown. And I gave you a graphical way of doing that. And I'm going to go ahead and focus on the graphical way of doing it. I think it's more beneficial. If you remember that behind that is that statements of equality that make conversion factors. Remember we said, like, we're given so many moles of one reactant times a relationship between the moles in the balanced equation of that reactant, and then on top what we're looking for to multiply that out. I just think the graphical way of seeing it is more beneficial for you. It's the same thing. Remember, it produces the same result, it produces the same multiple, but it's a way of seeing it rather than mentally calculating it. I just think it's better that way. And what I'm going to do today is just kind of offer to you that as you go through this module, they go through specific cases and present different ways of looking at either known or unknown reactants and known and unknown products. But if we use this technique of looking at and analyzing a reaction equation, you kind of get a big picture of what's happening across the board. If you remember, for example, that I said that a balanced reaction equation represents the ideal formula, the perfect recipe. I'll use ideas like that. The perfect recipe. That this and this combine in these proportions to produce this and this in those proportions. And that you get your statements of equality from your balanced reaction equation. Today we're going to go with this idea of fully analyzing chemical equations, which starts on, relating products to reactants on page 283. Page 283, we're just going to go ahead and start with a reaction equation that they give us here in the book, which uses ilmenite. That's that 2FeTiO3. It's got iron, titanium, and oxygen in it. So 2FeTiO2 plus 4 hydrochloric acid plus chlorine molecule reacts to produce 2 iron trichloride plus 2 titanium oxides plus 2 water. Okay, so there's the reaction equation that we're going to be dealing with. We go through and see if it's balanced, and we should see pretty quickly this is balanced. So let's check it. 2, 2, 2, 2, 4, 4 hydrogens, 4 hydrogens, 6 chlorines, 6 chlorines. Okay, so it's balanced. Right. Now, given that this is a balanced reaction equation, this is our perfect recipe for the production of these products given these reactants. And it's from this balanced reaction equation that we come up with our statements of equality. In other words, how are they related to each other proportionally? Remember I said that the equal sign doesn't literally mean they're the same thing, but it means that they're related in these proportions. If I have 2 of these, when I say 2, I could be saying 2 molecules, or 2 moles of molecules, or 2 dozen molecules, or 2 score of molecules, whatever the units are. But if I have a relationship, a proportion of 2 by count, not by mass, by count. If I have 2 of these and 4 of these and 1 of these, that they react together to produce 2 of these, 2 of these, and 2 of these. All right. Remember when we did the graphical way of analyzing the equation, what I said was if you're given a certain amount, you're going to drop a vertical line from the 2 molecules that are in question. Like if I said, let's relate this molecule, this ilmenite, let's relate this, and I drop a vertical line from the coefficient. Let's relate this to this. Okay? What I'm going to do right now is use that same methodology, and I'm going to go through and relate everything to one another. And I hinted at this in one of our classes. I'm just going to show you the relationships between them. Okay? Let me go ahead and draw a line, because I'm going to relate all of them. Let's come up with the multiples. In this balanced reaction equation, if I'm analyzing from here to here, what is my multiple going to be between those two? 2 to 4, right. This is what I'm looking for. Thanks, right. So there's 2 to 4, right? That's my relationship. You see that? It's my 2 to 4. Let's look at the next set. This is 4 to 1. Next set, 1 to 2. And from 2 to 2, it's also 1 to 1, right? And 1 to 1. All right. We can check it real quickly to see how these multiples work. Let's say that we were given the ilmenite, how much we have of this molecule. And we said, well, how much of every other molecule would we need to produce how much of every given molecule over here? Let's work the multiples from left to right. So if I said that I was given, let's make it simple so we can compare real quick. Let's double it. Let's just double it. Say that I was given 4. Okay? As I move from here to here and use my conversion factor, what's my multiple going to be? Now, as I hit across here, hit the first number and drive it under, right? So the 2 to 4 becomes 4 over 2, which is multiple of 2, right? 4 over 2, same as 2 over 1. If you want to write it as a fraction, that's fine, just to keep it straight. It's a 2 to 1. A 2 to 4 is the same as a 1 to 2, which is a multiple moving from left to right, a multiple of times 2. This would give me 8. Now, working again from left to right. I hit my 4, drive it under, my multiple becomes 1/4, which gives me how much? 8 times 1/4 becomes 2, right? Times, or excuse me, yeah, 2. 2 over 1 times 1, 4 times 1. Okay? Remember, I started with twice as much, and I have twice as much, twice as much, twice as much, twice as much, twice as much. Now, let's suppose that I wanted to relate this first molecule with chlorine, just directly. Let's pretend that I just draw this line, come down to the chlorine here, right? I'm relating across this way. And we're given an amount of ilmenite that we need. Let's say, for example, that it is still going to be 4. Let's say we're using 4 again. We're given 4 moles of ilmenite. And we want to know how many moles of chlorine we would react with that. How much would we need? Well, this is my unknown, right? And I'm driving towards my unknown. We're going to go ahead and put our relationship between the coefficients. It's going to be 2 to 1. Everybody see that? It's a 2 to 1 relationship. And since I'm moving from this known to this unknown, I'm moving in this direction, I hit this, I drive it low, my multiple becomes 1/2. And in process, this unknown becomes 2. 4 and 2. Now, this is the mathematical side of it, for those of you that are math-oriented. How do we get this 1/2? It is 2 times 1/4 is 1/2. You see? So it's just showing you mathematically that these proportions work the whole way through. And by doing it this way, by understanding these relationships, these multiples that you can create, by given any one, you can then compute any other. So if you had it this way, you could take a number, let's say you're relating hydrochloric acid to titanium oxide. You could sit there and go, okay, hydrochloric acid, it's going to become times 1/4, times 2, times 1. You could also say, my proportions are going to be 4 to 2, which is 2, right? 4 to 2 becomes 2. How do I get that? 1/4 times, so let's go over here. 2, it becomes 1/2, because if 4 pushes under, it becomes 1/2. So 1/4 times 2 is 1/2. So again, whether you do it, get the relationship directly, or whether you relate them all to one another and then multiply the fractions across, it comes out to be the same number. So if this makes sense to you, fine. If not, just stick with this one. Stick with the 2 that you're trying to relate to one another. Now, this idea here of of analyzing the entire equation or determine the amount of product or the desired amount of product for any given reactant takes this and works it the other way, right? If I'm given a certain amount of product I want to make, and I'm asked what kind of reactants do I need, rather than moving from left to right, I'm not going to be moving from right to left. So that's going to kind of change up how we do the work, but it's just the direction that we're moving across the number line, or the factor line. Now I'm going to experiment for a minute and try to teach this a slightly different way on how to determine the limiting reactant and what the consequence of that might be. Let's say here in the example in the book, for this reaction, they said, now if I only had 1 mole of hydrochloric acid, so let me go back here and say, if we're only going to use 1 mole of hydrochloric acid, rather than 4, we're only going to use 1. How much of the ilmenite would we need to react with that 1? We're moving from this in this direction, right? Here's our given, here's our unknown. So we're moving in this direction. Our multiple is going to be 1, right? It hits the 4, drives it under, it's 2 over 4, which is equal to 1/2. So if I use 1 mole of hydrochloric acid, it will react with how many moles of the ilmenite? 1/2. See that? Moving from here to here, my multiple would be 2 over 4, which is 1/2. Half of 1 is 0.5. Then how much chlorine would I need to react with 1 mole of hydrochloric acid? Well, in this case, I'm moving from left to right. My multiple becomes same as it was before, right? What is the multiple going to be here? Tyler, what's the multiple here? Don't know? What's the process we use? Come up with the multiple.
Oh, me?
No, I'm still talking to Tyler. Okay? Remember the process we taught was that you put the relationship, it's 4 to 1. Moving from left to right, the way we treat it is the first number we hit, it drives to the denominator. So as we move across from left to right, we hit the 4 drives under the 1, making a multiple of 1/4. So it's multiplied by 1/4. So we would need 1/4 moles of chlorine. 1/4 of a mole of chlorine and 1 mole of hydrochloric acid and 1/2 a mole of ilmenite. Because the proportion here is, this is 1/4, this is 1/4, this is 1/4. To produce how much of each of the molecules. So if I react to 1/2 a mole and 1 mole with 1/4 of a mole, it's going to produce how much? Again, we'll move across in that direction, right? So here, the multiple, we're moving from left to right, the multiple here would be 2 over 1, right? And so that would produce 0.5 moles of iron chloride, and it's 1 to 1, so these are all going to be the same. Yes, sir?
How do you know when to go do it from left to right?
You're always going to be moving from your known to your unknown. So in the case here, I was given 1, and I was trying to figure out how much of this. My unknown was in this direction.
Oh, okay.
From here, all my other unknowns are in that direction. Okay, so that's how it lays out. Now, here's the deal. In the question, they said, what if only 1 mole of hydrochloric acid were used? If only 1 were used. Right, so I say, okay, if I only use 1, right here I've said, if I only used 1, this is how much it would react with, and how much it would react with, and how much it would produce. Right? Where is my limiting reactant at? What am I going to do? How do I know which one is my limiting reactant? In other words, if I only had one, I ignore this, and I only have one, but I still have two of this, how much did I actually need? Half. Did I run out of this? No. Over here, I only needed a quarter, but I had one. Did I run out of this? So I know that this is my limiting reactant, right? This is the one that's going to run out. The next question says, what if you used 5 moles of hydrochloric acid? Well, if I used 5, how much would I need of the ilmenite? Again, the multiple is still going to be the same. It's still going to be times 1/2. And I go in this direction, I need 2.5 moles of ilmenite. And as I move to the right, I've got 5 moles of hydrochloric acid. How many moles of chlorine do I need? Well, it's still going to be 1/4 of that. So I need 1.25 moles of that. Now, I need this much, and I used this much. This is my use, right? I need 2.5. Do I have 2.5? No, I only have 2. Do I have 1 1/4? I only have 1. So I'm going to run out of both of these before I run out of this. How much am I going to produce? Well, do you see over here that we're producing less than we did in the perfect recipe? We're producing less than we did in the balanced equation. But do you see down here how we have more of one? So how much are we going to actually produce? Think in terms of the lab we did on Friday and the way it should have turned out. Just so you know, I'm going to get bigger size balloons. We're going to do it with 2-liter bottles and balloons that can hold the full complement. Because what we ended up happening was not the full reaction, so the magnitude was off. We're going to do it again so we can see it all. But what was the principle behind the lab on Friday? The first one, we added some baking soda, and it reacted, but we didn't have enough baking soda, and so we were limited by the baking soda. On the second one, we had the same amount of vinegar, but we added more baking soda, so we got more product. And on the third one, ideally, the way it worked is we had even more baking soda, but it would produce the same amount approximately as the middle one. And why was that? Because we eventually ran out of the thing that was being held constant. We ran out of it. We didn't have enough acetic acid. Okay? So in this case, we have a certain amount that will produce a certain amount. Here we're asking for less of one, and we've got plenty of everything else. And so our amount produced is going to be less. But here's the deal. If we have limiting reactants, we're only going to produce as much as those limiting reactants will allow us to produce. Okay? In this case, it calls for 2.5, and it calls for 1 1/4. How much do we actually have? 2 and 1. How much are we going to produce? We're going to produce this much. We require more than we have, and we require more than we have. So even though we use more of the hydrochloric acid, we can only produce as much as our limiting reactants will allow us to produce. Okay? Here, the limiting reactants, we've got 2 of them. Both ilmenite and chlorine are going to run out. Do we know hypothetically how much we could produce? Yeah, sure. Hypothetically, we'd say, well, if we use this much and this much, we had this much, we hypothetically would produce that much. But you know what? We don't have this much. In reality, we only have this much. And so what we do produce is according to the balanced reaction equation. But one thing we have a surplus of, and everything else we have the same amount of. So we have a surplus here, and we're limited by these 2. So our production can only be as much as our balanced reaction equation would allow us. So if I combine 2.5 moles of this, 5 moles of this, excuse me, if I combine 2 moles of this, 5 moles of this, and 1 mole of this, what am I going to produce? It's still going to be 2, 2, and 2. And I'm going to have, on the back side, I'm going to have leftover hydrochloric acid. Because I have too much compared to the balanced reaction equation. I have too much. See that? And hopefully, again, as we do on your own and other practice problems, it'll make more sense as we go through this. This is the kind of thing where you have to see it and do it a few times again, motor memory and also working it out, where it starts to make sense as you do it. So hopefully, at least in here, the big thing here, the process, how do I go from a known to an unknown? I do that by computing the multiple. What's the multiple going to be as I move from one direction or the other? How to compute it correctly? And then analyzing the equation to see, okay, what is my limiting reactant? Whatever's limiting my reaction, that sets how much product I'm going to make. Whatever limits the reaction. In this case, my limiting reactant was less, and so I could compute what that would be something less. In this case, I've been given one of my reactants and I've been given too much, which makes the other my limiting. So the most I can make is this much on my balanced reaction equation. Let's try, let's look at example A3 as a way of maybe approaching this a little bit more deeply. So we've got ethanol and sulfuric acid to produce ether and persulfuric acid. Let's go ahead and so 2C2H6O plus H2SO4 react to produce C4H10O and H4SO4. So a chemist wants to make ether or ether, however you say it, right here. I've heard it said both ways, as an anesthetic, and uses the following reaction, okay? If the chemist needs 134.9 moles of ether, so what we're going to do, first go over to the ether, find the ether, here's the ether. The chemist needs 134.9, right? The chemist needs 134.9 moles of ether. What's the minimum number of moles of both of the reactants, right? Sulfuric acid and ethanol. I'm going to connect them. How much of that do we need? So I note the molecules that are in question. I draw a vertical line below them. Then I write down, we're talking about moles, I write down how many moles of the known we're given. We're given that the chemist needs to produce this many moles of that molecule. And now using stoichiometry, these stoichiometric coefficients, we're going to relate how much we need to produce back to how many of each of the reactants we need to have. Right? We need at least. That's why it says we need at least. Because if we have at least that much of each reactant, we can make at least that much product. So let's go through the method that I was showing you on computing the factors to get us from 134.9 across to the beginning for both of these molecules here. So what's my relationship between the sulfuric acid and the ether? Okay, so I have a 1-to-1. See that? The 1 and the 1. It's a 1-to-1 relationship. So my multiple in both directions is 1, right? My multiple in both directions is going to be 1. So to produce 134.9 moles of ether, how many moles of sulfuric acid do I need? 134.9. Okay? And that 134.9 moles of sulfuric acid has to react with how many moles of ethanol? What's my relationship here? 2-to-1. 2-to-1. And I'm moving in this direction because I'm going for, I now have a computed known to an unknown. So my multiple becomes 2, moving in that direction. My multiple is 2 when I'm moving from right to left. And so what it's saying is I need twice as many moles of this, twice as many moles of this than of this. I have 134.9 computed, times 2, it's 265.8 moles. 269, excuse me. 269.8. So looking at the balanced reaction equation, whatever number of moles of ether that I'm going to produce, I'm also going to produce how many moles of per sulfuric acid. Didn't ask us that, but how many would we produce over here? Right, because it's 1 to 1, right? 1 to 1, the same amount. So we would also produce 134.9 moles of the per sulfuric acid, because they're related 1 to 1, 1 to 1, 2 to 1. And you see, hopefully from here also, that if we skip this intermediate step, I could do one that would relate these two. I could do another one that would relate these two. I was given 134.9, and I know that from ether to ethanol is a 2 to 1 relationship, and the multiple is 2, and it would work out to be the same mathematically, because 2 times 1 is 2, moving me from here to here. If I multiply the multiples, 1 times 2 means it's a multiple of 2. Any questions on the example, on how they computed those answers? You can see that what they did on the example, if you look at the lower part of 284, where it shows you 134.9 moles of ether times 2 moles of ethanol over 1 mole of ether. What they've done there is as I do it graphically, you're just relating what they are proportionally. You look back at your balanced equation, 2 and 1, a multiple of 2 over 1. Where does that 2 over 1 come from? Implied in here, in my multiple, is 2 moles of ethanol per 1 mole of sulfuric acid. You see that? So where I have just 2 and 1, you should be able to see in your mind 2 moles of this and 1 mole of this. And moving from left to right tells you which is on the top and which is on the bottom, based upon the direction you're moving on the equation. So this is 1 mole of sulfuric acid per 1 mole of ether. And this is, over here would be 1 to 1, 1 mole of ether per 1 mole of per sulfuric acid. So it's the same type of concept. If you understand moving left to right and how to compute the multiples, then if you were to put the units in here, you would basically have what you have in the book. For example, like I said, this is 2. This would be 2 moles of C2H6O per 1 mole of H2SO4. That's just writing all the units. You get the numeric correct, just knowing it's times 2. Technically, what are we doing? We're relating moles of ethanol to moles of sulfuric acid. All right, we are down to on your own 8.3. Why don't you go ahead and work that. 8.3, work it into your notes, and that'll be probably the day.